everyone. Good evening. Thanks for joining again. So today we'll be starting the week two session of other sets marketing system and application. So I'm a teaching assistant. My name is Monica. I'm a PhD student at the Prime Minister's Research Fellow for the Indian Institute of Science. Just give me a moment, please. Yes. So your instructions for today is the first one is the session is being recorded. Kindly be respectful during the session. Use any words against anybody during the class. And please put all the questions in the chat box during the session. And in this session, so I will mostly discussing regarding the assignment questions with a little bit of theory. Okay, and I'll also be helping you with your MATLAB and coding. After the 12 weeks, I will be taking one additional class. Please, you wish me to cover any existing or additional topics related to this course. Okay, so for this week's summary, we have started with left-right membership functions, where we have three parameters, okay, which determines shape of the membership functions. And these parameters are alpha, beta, and gamma. So the left-right membership, that is X, is defined with these three parameters, but we write it as C, alpha, and beta. Right? And when X is less than or equal to C, and when X is greater than or equal to C, we have different function equations. So for X less than or equal to C, this is a function, and for X greater than or equal to C, this is a function. The defined range of this left-right membership is 0 to the Fn and F are increasing functions. So with respect to X, decrease. So this graph right now, which I'm showing, so this is an example of decrease function. Okay, so what for these Fn and Fi functions? When we put the values in it is going to be equal to when X tends to infinity, then the values of this function are equal to 0. So that is both F power and F as well. Here, and the point C is point where the membership function is at the peak, that is at the highest, and the maximum membership function is at the So at the point C, we have the mu whereas alpha, the leading parameters that controls the width of the left region and the right region respectively. So if reason in the sense when X is less than or equal to 0 and the beta, the right region is less than X. So if this is a graph, this at the peak, this is the value of C. This side is alpha. MATLAB discussed during the class. Code from there, and it's a similar code that we have discussed in the last week's problem solving session. So you can try it some so see and figures so that you know the difference. Clear so far? So that is the first function, that is the left right. Now we see that in pie-shaped conversion. So in this pie-shaped conversion, we have two different functions, that is and in this case, phi1 will be having parameters, that is A and E. Phi1 is defined fundamentally. Phi1 is x minus A by equals 1. We think the observe here is that this membership function becomes 1 when this becomes 0. So when this becomes 0, then x is 0. Okay. So we want to find the membership function that is 0.5. Then x minus A by b equals 1. should be equal to, sorry, so that the denominator is good. So this answer when x is a is b and x is equal to x. So these are the two observations you need to keep in mind when you're dealing with pi function. When you're and then we have another pi shaped function that is pi 2, where we have four values or parameters, that is LW, LG, RT, and RW. Where LW and RW are the feet of the membership function, and LE and R are the shoulders of the membership function. So they are defined they are divided into three parts. That is where x less than L. That is shoulder at side shoulder of the membership function. And x lies between LB and RB, and when x is greater than RB. That is the right side shoulder. So three is where you get all the values together. Like find out what is the relation. But x lies the shoulder, then just so this is your graph. This is this is LW. This is sorry, LW, and this is in between. So in between your LP and WP, the values are always good. And for the rest, you need to calculate using the other two functions. And then we have another membership function called open right membership function, where we have two parameters, that is alpha and beta. Since open right, as the name suggests, it is completely open on the right side of the graph. That is, when we go to x equal to infinity, it keeps having the value 1 to its membership function, right? And and it is defined by two parameters, alpha and beta. When x is less than alpha, it is always equal to 0. And when x is greater than beta, it is always equal to 1. And in between that, you can calculate the membership value as x minus alpha by beta minus alpha. Right? For the graph, as when x is less than alpha, that is when it falls in this whole region. When x falls in this whole region, then that is equal to 0. And when x is greater than beta, that is when it falls in this region, it is equal to 1. And anywhere in between, it is going to be a linear relationship, right, with x minus alpha by beta minus alpha. Okay, you will be given the alpha and beta values, and also you will take the x values at different intervals, and then you can put it in that function and find the values of it. Okay, so this is another way of finding the membership function values. And then we have left open membership function. So that is similar to the previous one, but this time the left side is going to be completely open. That is, when x is less than alpha, it is going to be equal to 1. And when x is greater than greater than or equal to beta, then it is going to be 0. And anywhere in between is going to have a linear relationship, okay, with a negative sign. Okay, so that is same as previous. And the last membership function that we are going to discuss is the S-shaped membership function. So in this also we have two parameters, A and B, where A defines the feet and B defines shoulder. So what you can do is you can kind of draw an S-shaped function in the graph and then try to figure out the values, right? So when x is less than or equal to A, this A is here, then it is equal to 0. And when x is greater than B, it is going to be 1. Okay, so here is 1. And anywhere in between, if you take a plus b by 2, the mean value of a and b, when x lies in between a and the mean of a plus a and b, then you are going to get a membership value of 2 into x minus a by b minus a equals square. Whereas if you are taking it in between the mean of a plus, a and b and b, then it is going to be 1 minus b. Okay, so that is 1 minus 2 into x minus a by b minus a whole square. The rest values are equal to 1. So these are the total membership functions that we have in this entire lecture. So let's go back to last week's class and see what we have discussed before and what we have discussed today, so that we'll have a complete understanding of the membership functions that we have. Right? Just a second. Yes. So last week we have discussed the triangular membership functions, right? Where where we have taken the minimum of x minus a by b minus a, or c minus x by c minus b. And then we have taken the maximum in between the previous value and then of the zero. So that is for the triangular membership function. As soon as the triangular membership function is done, then we have gone for a trapezoidal membership function, right? So in the trapezoidal membership function, we have seen when the values of when the membership value becomes 1 and when it becomes 0, and how do we identify the maximum value of x and all of that. Where we have seen a lot of examples previously, and then we have a Gaussian membership function, and today we have discussed left-right membership function, right? And then we have discussed pie-shaped membership function. So this basically looks like a pie, right? So that's why it's called as the pie membership function. Then we have open right membership function, that is the right side of the entire membership function is going to be the same. That is equal. We have the one keeping the left side being open, that is equal to 1. The membership value is always equal to 1 when x is less than or equal to alpha. And then we have discussed the S-shaped membership function. So these are kind of membership functions that we use in in most of the applications that we are using today in life, and we'll be seeing these again during the next few classes as well. So to have a better understanding, we'll also cover the nomenclatures, right? We discuss all different types of nomenclatures, and it does support for crossover points, height, normality, subnormal fuzzy sets, fuzzy singleton, alpha cut, strong alpha cut, cardinality, bandwidth, and all such were discussed. Okay. If if I say this is my graph, okay, and then if I'm saying I want to find the support of this particular membership function, then it lies in between this point to this point, where the values are non-zero. When mu a of x, that is a membership value of a, of x, is greater than 0. Supposed to put them as a circle. So these does not include when it is equal to 0. So all the values in between these, all the values of x here are my support of a. So if I'm calling this membership function as membership graph as a, then all the x values when the membership function is not equal to 0 is called as the support. Okay. Right. Then let's look at core. This one. Feature. So the x-axis represents all the x values and the y-axis represents the membership values, membership function values, right? And let us call this graph, membership function graph, as A. Okay. So here you can, you know that the highest membership value is equal to 1 and the lowest is equal to 0, right? And let us call this as A and this as B. Okay, and this point as x1 and this point as x2. All the x values when the membership function is equal to 1, that is all of these values here. So that is called as the core of A. Okay? All the values in between x1 and x2. Okay, when for a given value of x, if the membership function value is equal to 1, then it is called as a core of A. Right? For example, let us say I have a set for, let us say x equal to 2, the membership value is this. For x equal to 3, the membership function is 0.7, and for 4, it is 1, and for 5, it is 1, and for 6, it is 1, and for 7, it is 0.5 again. Then the core of A is equal to 4, 5, and 6. That is when the membership function values are equal to 1. Okay, so this is called as the core. And let us again look at what is the support for this particular example. So support A is equal to, the membership function should be non-zero. So in this given set of A, we have all the numbers as non-zero. Hence, the support of A is 2, 3, 4, 5, 6, and 7. Right? So this is called as core of this membership function. Hope I'm clear so far. I hope I'm clear so far. Okay. And then we have crossover points. So again, for a given graph, x and y, so where x are different values that input values that we take, and y is a regression function value. Okay. Let us say this is our graph. The highest peak point is equal to 1, and the lowest is equal to 0. For a given point, so let us say I want a membership function value of 0.4 or 0.3. Okay, let me just draw a line. Let us take for 0.3. If I'm saying this is 0.3, then 0.3 occurs 2 times in this membership function graph, that is at this point and at this point. Right? Let us call this one as x1 and this as x2. Right? Then we call x1 and x2 as crossovers of A. The crossover point is the point is the point x in the universe of discourse, that is capital X, at which this membership function in f of x is equal to 0.3 in our for example. Okay, but usually for crossover we take 0.5. So let us say this is 0.5. Okay, so when the membership function is equal to 0.5, then we say the crossover is at x1 and x2. Okay, so we have to write it in as in our representation form. Then we say the cross of A is equal to x such that u of A of x is equal to 0.5. Okay, so finally we can say for the given fuzzy set A with the universe of discourse of capital X, the crossover of A is equal to x1, x2. Equal to x1, x2. Okay, so that is a crossover point. That's what we have said. So we discussed support, we have discussed pole, we have discussed crossover point, and then let's go for height. Height of the, and let us say this peak is at 1. Then for this particular function, the height is equal to 1. Let us take a different example of a different here. Let us say this value is 0.5, then the height of that function is equal to 0.5. Okay. Let us see another one. Let us call a triple seven. And this value is 0.7. Then the height of this is equal to 0.7. So whatever the maximum membership value is, that is what is the height. Okay, and if we have to represent it, then we can write it as height of A is equal to maximum of your x. Okay, if from in the last class we have discussed what subnormal fuzzy set is, right? So you if the height of A less than 1 or that is equal to 1, then we call it as a subnormal fuzzy set. So in a given fuzzy set, if we do not have a member for any given value of x, if we do not have a membership value, then it is termed as a subnormal fuzzy set. Okay, I hope I'm clear. So in the previous graphs, all the 3 graphs, if we look at the green color graph is a normal fuzzy set, and whereas the yellow and the violet ones are subnormal fuzzy sets. That is the heights and the subnormal fuzzy sets. Okay. So what is the next one? So we have discussed height, we have discussed subnormality as well. So let's look at normality. So a fuzzy set is considered normal if its core is non-empty. So its core is non-empty. So what it will define core as? For a given graph, for all the values of 1, it has this x1 to x2 is called as the core, right? When a membership function value is equal to in between the different values, then it is called as the whole set is called as a core, right? So now we are saying we want the core to be non-empty. That is, at least one value should have the membership value of equal to 1, right? Then it is called as a normal fuzzy set. Okay. So this is clear. Then let's look at fuzzy singleton. I'm not going to helps the NTL from the service show. So I request you kindly go through those videos in detail. So this is basically to give you a gist or a summary of the entire week so that we can discuss the problems. Okay. Not going that deep into that point. Okay. So let's discuss about fuzzy singleton. So a fuzzy set whose support is a single point in universe. Okay, so that is when mu of a of x is equal to 1 of a single point, then we call it as a fuzzy singleton. So just look at the graph. X1 and this is 1 and u of x 0. Right? So we have only one point, that is this line x1. Okay, so this is a fuzzy set A or a singleton, right? So this is only going to be the support. This is only going to be, and this is only going to be the core of the fuzzy set as well. And then alpha cut of a fuzzy set. You can also put it as y, and then we have x. Is it being clear to you? Any questions so far? So let us take a triangular membership function. Right? This peak is, let us call it as 1. The alpha value here in between. Let us say alpha is equal to 0.4. Right? This alpha equal to 0 is cutting the triangular membership function at 2 points, that is here and here. Call it as A and B. So A alpha, that is all the values that has a membership value of above alpha equal to alpha, that is 0.4 here. Then we take that as a alpha level set. That is all the values that lie in between A and B here, A and B here. So that is all these values. These are called as alpha level set. Level. So all the values in between A and B are called alpha. So that includes AB as well. So the set is equal to A, all the values in between, and then ends with B. So that is alpha cut. Now we also have another alpha cut called a strong alpha cut, where we do not include the A and B values. If we have to write a representation for this alpha cut, it is A of alpha x such that of A of x is greater than or equal to alpha. But if I take the same to alpha, strong alpha cut, what I have to do is should be greater than alpha. So the set will be all the values that come in between A and B, but and does not include AB. So that is the difference between alpha and strong alpha. Let us look at an example to understand. So A equals 5, 0.6, 0.7. 0.9, 8, 1, 0.7. So let us say this is my set, and I'm giving the alpha as 0.4. So here alpha is equal to. So this membership value is less than alpha. So we're going to take this. This membership function value is greater than the alpha. So we'll take 6. Then this again 7. Again 8. The value is greater than alpha. So 9, 10. And we are not taking 11 because the membership function value, that is 0.3, is less than 0.4. So this is A of alpha. Let us add one more. 0.4. And we'll add 12. Okay. Now, if we are taking strong alpha, then we'll take 6, 7, 8, 9, and 10 only. We are not going to take 12 because we need the membership value to be greater than alpha, not greater than or equal to alpha. Whereas in alpha cut, we take it as equal to greater than or equal to alpha. In strong, we take only as greater than alpha. I want you guys to try this experiment, this one out. So I need you guys to find. Just want to try this a bit. Then 0.3, 0,
I when will reach electronics?
13, 0.7. Okay. So I want you guys to find the support.
We know it will drop. We just at the expense of electronics. This time the Infosys process will come out again
Four, and
electronics it internally.
then for alpha equal to 0.3, find alpha cut and strong alpha cut. And also the crossover. So this one alpha should be equal to 0.5. Right? So I want you guys to, for a given set, Salsi set A, find support 4 and alphabet, strong alphabet, and crossovers. And when alpha equal to 0.3 for alphabet. So 4 for, and also the height. And if this is a normal set or not a normal set. Okay. So I'll give you time till 6:38. At 6:38, I'll get the answers again. Okay. Nice everyone. So it's good. Great answers, everyone. So let's do it once again. Okay, so if anyone has not gotten the answer, just write out now. Okay, for support, we should be having the membership values as greater than 0. So we have the support set to be 6, 7, 8, 9, 10, 11, 12, 13. That's it, right? So that's the support. And for the core, we need to have the membership value as equal to 1. Okay, I randomly gave these values, so there are a lot of up and downs here. Okay, so we have the membership function, membership core set between 10 and 12 because those two are the only x values that have a membership value of equal to 1. Okay, so for alpha cut, a of alpha is 0.3. The set is equal to, we are not taking 6 because it is less than alpha. We are taking 7 because it's greater than alpha. We are taking 8 because the membership value of it is greater than alpha. And we are taking 9. Then we are taking 10, taking 11 because it is equal to alpha. And then we are taking 12 and then 13. And if we are saying we need strong alpha cut, we have 0.3, then it is almost equal to the alpha cut, but without one value that is 11, because the membership value is equal to 0.3 for that. Okay, so it is 7, 8, 9, 10, 12, and 13. So we are skipping 11. Okay, so this is strong alpha cut. Crossover, that is at alpha equal to 0.5, we have at 7 and at 9. Right? Anywhere else? No. Right? So we'll crossover the 9. And coming to the height, height is the maximum value of all the membership values of that particular set. And the highest value that we have is equal to 1. So height A is equal to. And is this a normal or not a normal or a subnormal fuzzy set? It's a normal fuzzy set because we have a value that is equal to the, which has a membership value equal to 4. That is at 10 and 12. Right? Hence it is a normal fuzzy set. And then we have normalization. So normalization is we take a fuzzy set of membership value and divide it with the height of the entire set for that particular x value. Right? We know the representation, right? We write as mu of a by x. Right? Same way, what you do is in place of mu of a, you write it as mu of a by height of a. You're basically normalizing the entire set so that whichever has the highest value, that will become 1. So you are converting a sub-normal fuzzy set into a normal fuzzy set using normalization. Okay, and then we have convexity. So in convexity, we have the x values, x1 and x2, and then we have another parameter called as lambda. So this lambda can be any value in between 0 and 1. Whereas x1 and x2 are two generic variable values. Okay, so to know if a fuzzy set is a convex one or not the convex one, you need to use this particular condition. If this condition needs to be satisfied, if it is satisfied, then we call the fuzzy set as a convex fuzzy set. Okay. Uh, we we have covered alpha cut and strong alpha cut, right? So there are some other terminologies which are being. Let us look at them called cardinality. So it is a measure of the number of elements of that set. number of elements in a set. For example, if I'm saying for a given key, I have 6, 0.7.3, then the cardinality of this set is equal to 2. Okay, however, if you're taking a continuous fuzzy set, you will have infinite numbers. Then we have bandwidth of a set. So So to calculate the bandwidth, the first step that you have to do is to find the crossover points. First, to find the crossover points. If you are having multiple points, then what you have to do is you have to take the extreme crossover points. And then take the difference between both of them. Okay. So you take the modulus and then you take the difference between the points x1 and x2, then x1 and x2 extreme crossover points. Okay. Okay. And another term is we have equality. So we call two sets are equal when their memberships are equal to each other. So mu of a of x is equal to of b of x for all values of x in capital X in the universe of disclosure. Okay. So all the membership values of an element x in the fuzzy sets A and B should be equal to each other. We call them as equal fuzzy sets. Okay. And another final one is containment subset. So containment is when you can say the membership value of one less than or equal to membership value of another subset B. Sorry, fuzzy set B. Okay. But in case if you are using A belongs subset B or equal to. So that is containment. It is an example containment. Say 0.6 by 1 is 0.9 by 2, 0.3. Yes, it is called that as A. And let's take another fuzzy set B, 0.9 to 0.5 of 3. Okay. So now let us compare the membership values of A and B. So for x equal to 1, A is 0.6 and B is 0.9. That is, A is less than B. Right? And then for x equal to 2, we have 0.9 of A and 1 of B. And for the value of A is 0.3 and that of B is 0.5. So all these membership values of A is less than membership values of B. Hence, we can say that A belongs to or equal to subset of B. So this is called containment or in general terms, subset. Okay. Another one that I forgot is complement. So in a normally classical set, what we take the complement of the whole groups minus the whichever set we are using, right? So if we denote it in terms of A dash. Here, what we are doing is we are taking u of A of x bar is equal to 1 minus u of A of x. So to take this example, that A as this example. Now, if we were to find the complement of A, then it is 1 minus 0.6, 1 plus 1 minus 0.9, 2 plus 1 minus 0.3 of 3. That is equal to 0.4 of 1 plus 0.1 of 2 plus 0.7 of 3. Right? So this is a complement. I hope you understood so far. I will give you another question. So bigger that A equal to 0.1. Please note it down along with me so that the question will be lengthy. 6 0.4, 7 0.5, 8 0.6, 9 0.7,
Nice one.
10 0.8, 11 1, 12 0.7, 13 0.6, 10 0.6, 15 0.5. Okay. Let's find all the values, all the things that we have done from the beginning. Support 4, crossover point, right? Normality, alpha cut, and for alpha, what value shall we take? Shall we take 0.4? Okay. And then strong alpha cut. Okay, and alpha equal to 0.4. And cardinality. And then bandwidth. Okay, we'll also this sorry, complement. Uh, find all these 10 function. Oh, sorry, all these 10 for a given fuzzy set A. Okay, let's take time to 7, 10. Okay, and we'll again with the answers. Okay. Hey guys, so I might use network again after some time. So I will come back to this question again. But there are other theory questions that I would like to discuss from the previous year's assignment. Okay, so let's go through them. So which of the following is a disadvantage of open right membership function? Please give your answers. So what do you think is the right answer for this? What is a disadvantage of open right membership function? So let's draw a graph of this. So this is the open right membership function. So what do you think is one of these advantages? Or what are the what is the main disadvantage of this membership function? You would option D is your right on Kuch. So the answer is option D because the open right membership function extend infinitely to the right, which can lead to uncertainty in setting the boundary of the set, right? Hence, that is one of the main disadvantages of open right and also with open left. Okay. So the uncertainty will be there on the left side for a open left membership function, but whereas for right, it is for the right side. Okay. So next question. What does an open left membership function imply about the leftmost part of the function? Okay, so this is the open left membership function. So what do you think is the implication about the leftmost part? So that is almost same as the previous answer. Option B. Answer graduates. We are discussing about the leftmost part. Okay, so this basically extends infinitely to the left. Next, third question. What characterizes an open left membership function? D. None of the above. So for the open left membership function, it extends infinitely to the left. Okay, and whereas for the open right membership function, it is an infinite extension to the right. Okay. So let us see this question. Given an open left membership function with a peak at x equal to 4, if the degree of membership at x equal to 2 is 1, what is the degree of membership at x equal to 1? Okay, so let us draw the diagram
National Highway 4, National
where
Highway 48.
just try to draw the graph of this x. So it is saying if I give open left with a peak at x equal to 4. At x equal to 4, let's call this as 4. This is the peak. The degree of membership of x equal to 2 is 1. Then at x equal to 2, it is 1, right? What is the degree of membership at x equal to 1?
ಅಲ್ಲಿಲ್ಲ ಅಂತಪ್ಪ ಅಲ್ಲ ಅಲ್ಲಿಲ್ಲ ಅಂತಲ್ಲ ಅವನ ಹತ್ರ ಇಲ್ಲ ಅಂತಲ್ಲ ಏನಪ್ಪ ನೀವು ಒಂದು ಡೀಟೇಲ್ ಹಾಕಿ ಮಾಡ್ತೀರ
We have it is said that at x equal to 4, we have the peak, and at x equal to 2, the membership value is 1. then what will it be for x equals to 1? And it is given that it is an open left membership relation. Hence, this is the graph of it, right? So for x equal to 1, we'll have the membership value of 1.
ಇಲ್ಲಮ್ಮ
Okay,
ಇಲ್ಲಾಗ್ತೀಯಾ
just a second.
ಮತ್ತೆ ಇಲ್ಲೋಗು ಅಂತ ಹೇಳು.
Okay, so let's look at the sixth question. So in a left-right membership function defined by the parameters a equal to 2, b equal to 3, and c equal to 5, what does parameter c represent? So if you take a look at the left-right membership functions, let's go there. This, right? So for a left-right membership function, the value c represents the point at which mu is equal to 1. So the answer is C. The point where the membership value is equal to 1. Okay. So if you have two left-right membership functions with parameters 1, 4, 6 and 3, 2, 7, each function has a wider right region. So the width of the right region is determined by the parameter C. Okay. So in 1, 4, 6, the width is 6, while for 3 to 7, it is 7. Although the second function starts later, 146 has a larger right region width as per its configuration. Hence, 146 has a wider right region. Next question, in a Gaussian membership function, what does parameter nu represent? So the nu represents mean in a Gaussian membership function. For two Gaussian membership functions with parameters nu1 equal to 3 and sigma 1 equal to 2 and nu2 equal to 5 and sigma 2 equal to 5, which of the statements is true? So for lambda 1, sorry, for Gaussian membership function, the standard deviation is 2, and for that of the second, it is equal to 5. So whichever standard deviation is greater, that will have a greater width, right? So the width of the second function is greater because it has a higher standard deviation compared to the first one. Okay, let's look at the last question. If the standard deviation of a Gaussian membership is increased, what impact does it have on the function? So if it is increased, then the peak becomes broader. So increasing the standard deviation causes the Gaussian function to spread out, resulting in a broader peak and a more gradual slope on either sides. So the peak becomes broader. Okay, you can see this. You can confirm this using the Gaussian membership function in MATLAB. You can transformations and you can see how the plot changes for different values. Okay, so these are some of the previous questions. So let's get back to our previous question. Um, Now let's take time till 7:15 and finish off the rest. And once it's done, we will discuss the answers and we can end the class. Oh, so sorry. So, okay, let's just again, I'll just say everything. So for the support, we should have the membership value greater than 0. So we need all the values that are there in the subset, sorry, in the fuzzy set A, that is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 in our support. Whereas in the core, we have only one X value that has a membership value equal to 1, that is equal to 11, right? And this 11 is also a fuzzy singleton because it has only, there is only one element and also its membership value is equal to 1. And for the crossover point, 7 and 15 are the only 2 points that has a fuzzy membership value of 0.5. So those two are our crossover points. And for the height of the membership value A, it is equal to 1. Since we have the height equal to 1, it is called as a normal fuzzy set. If we have it less than 1, then it is a subnormal fuzzy set. Okay, so now let's look at alpha cut at 0.4. So 5 at x equal to 5, the membership value is zero point 0.1, which is less than 0.4. Hence, we are not taking that as into the alpha cut. And at 6, we are taking it even though the membership value is zero point 0.4, because in a normal alpha cut for a set, we take values greater than or equal to alpha. So then we have the points 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right? So if we are to find a strong alpha cut, strong alpha, then that is equal to 6. Sorry, 6 is the only one which will be omitted. And rest all will be there. 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay. So next, cardinality. Cardinality means the total number of elements in the fuzzy set. So we have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? We have 11 numbers. So the cardinality is 11. Now let's look at bandwidth. So bandwidth is the difference between the two crossover points, that is x1 minus x2. So our crossover points are 7 and 15. So modulus 7 minus 15 is equal to 8. Right? So our bandwidth is 8. Let's find the complementary of it. Let me bring down the question again. Okay. So now let's write the complementary part. So for 5, it 5 comma 1 minus 0 0.1, that is 0 0.9. Right? For 6, it is 1 minus 0 0.4, it is 0 0.6. For 7, it is 1 minus 0 0.5, which is again 0.5. Then it is for 8 and 1 minus 0 0.6, that is 0 0.4. For 9, it is 1 minus 0 0.7, so it is 0 0.3. For 10, it is 0 0.2. For 11, it is 0. For 12, it is 0 0.3. For 13, it is 1 minus 0 0.6, it is 0 0.4. For 14, it is 1 minus 0 0.6, it is 0 0.4. For 15, it is 1 minus 0 0.5, it is 0 0.5. So this is a complementary set. So if you look at it as a whole, you don't have any membership value that is equal to 1. Hence, this is a subnormal fuzzy set. Right? So later, if you have some time, you can also try finding all the above things, but it's complementary set as well, and see what weird answers you're getting. Okay, so what are the difference between this fuzzy set A and the complementary fuzzy set A? Okay, and see what are the crossover points, what is the support for height, and you all already have discussed that the complementary one is a subnormal fuzzy set, right? And also find alpha cut, strong alpha cut, cardinality. Cardinality will be the same because it's the same number of elements, and the bandwidth is also going to be the same, right? So yes, I would say so. Right. So, yeah, Tejas, I think, are you clear with bandwidth and complement right now? So I hope I'm clear with what I have said. So, right? If you are still not clear, please let me know. Okay. So, yeah. So I'm done with the content for today. In case if you guys have any other questions, please do message in the chat box. I'll stay in this class till 8, but I'm done with today's content. Okay. So that's all for today. If you have more questions, please put it in the chat box and others can leave. Thank you so much for joining and being really attentive and answering all the questions in the chat box. Thanks a lot, and I'm really sorry if there were any network issues in between. Okay. Thank you so much. Thank you so much for joining. I'll stay here till 8. You can still- no, you have to take the membership value to be 0.5 when you're looking for bandwidth. Okay? Bandwidth should always have a membership value of 0. So for first you need to find the crossover points in order to find a bandwidth. Okay, crossover points are the points that have a membership value of 0.5. Okay, then for bandwidth, what you do is you take the difference between both of them and apply a modulus to it. Okay, then that the value which you get after you do the difference, that is thank you very much. Any more questions, Jiru? Okay, I'll stay here till late. In case if one of you have any questions, just drop a message and I'll answer. If not, thank you so much for joining. First conversation, sure. Just give me a second. Okay, I'll take a simple fuzzy set. Okay, let us say let us write it in a different representation. 0.31 is 0.62 is 0.1 of 3. Okay, so now the height of A is equal to the maximum membership value, that is 0.6, right? examples, shall we make it easier for us? Let's take even numbers. A is equal to, we have this as our fuzzy set, and let us now for the height, it is 0.6. So for normalized one, what we do is you take each and everything, that is 0.2 divided by 0.61 less 0.6 divided by 0.6 of 2 is 0.4 divided by 0.6. 3. So this is going to give you 1 by 3, that is 0.33 plus 1 by 2 plus 3 equals 0.66. Right? 3. Right? So now A is basically a subnormal fuzzy set. Right? None of the values have a membership value of 1. Whereas when you do normalization, that is when you divide all of the membership values with the height, that is a maximum membership value, then you are getting one element has a membership value of 1. So it is basically becoming a normal set, normal fuzzy set, right? So this is the reason why we do normalization. And this is how we do normalization. I hope it's clear now. Are you clear, Jerome? It will be normal because you're taking one value, the same value you're dividing. You're taking all the membership values, you're taking the maximum value of all the membership values that are present, and you're dividing it. So at one point, you are dividing the same value over and over, right? Then you are going to get 1, right? So it's 0.6 divided by 0.6. It's going to be, because if you have a height of 0.3, and when you're dividing everything, you will always have at one element 0.3 divided by 0.3. Hence, it's going to be 1. So the whole point of normalization is to make a subnormal set into a normal one. Any more questions?